finding an antiderivative or discovering the antiderivative for yourself can sometimes be a lot more difficult than just proving the antiderivative, because taking antiderivatives is almost always more difficult than taking derivatives. And so if you wanted to discover this for yourself, you could remember that tangent is just sine divided by cosine. And then I would recommend a u substitution. What should I set u equal to?
Cosine of x.
That's very good. If I set u equal to cosine, then the derivative of u with respect to x would be negative sine. And that means I could replace the dx, or I could replace the sine of x dx with negative du. And then taking the antiderivative. What's the antiderivative of 1 divided by u? Yeah. And so the final answer here would be negative natural log of absolute value cosine x plus c. And like I said, maybe you memorized that. And if you have that memorized, the only thing you need to do to prove to somebody that's true is you just take the derivative of negative natural log of cosine x using the chain rule. But if you didn't have that memorized, this is how you could rediscover that for yourself. Similarly, if you had the antiderivative of cotangent, what you would need to do is remember that cotangent is equal to what divided by what? Cosine over sine. And I would recommend a u substitution. What do I set u equal to? Sine of x. And since you've already seen the tangent version, I'm not going to spoil the ending to this one. I'll let you work on that on your own time. And we'll move on and we'll think about the antiderivative to secant. So now I've got antiderivative of secant x. And I don't think you're going to be able to guess this one. Maybe you have it memorized, maybe you don't. But the tricky part here is that we are going to take the antiderivative of secant x times secant x plus tangent x divided by secant x plus tangent x. And you guys can tell that's just multiplying by 1, so it's not going to change the value of anything. I'm allowed to do this, but this is such a crazy trick because you're like, why? How would you even know to multiply by that? And I think the answer is you really wouldn't know unless somebody had showed you, right? This is a very unusual thing to do. But if you do this, then I'm going to end up with the antiderivative of secant squared x divided by secant x plus tangent x. And then separately, we'll think about what it would look like to take the antiderivative of secant x tangent x divided by secant x plus tangent x. Sorry. Got a little ahead of myself. I don't think I should have separated that. I think it would be smarter to instead say secant squared x plus secant x tangent x. Now we might do a u substitution. And what is the u in the u substitution? So we could try that. We could say secant squared. The derivative of u with respect to x would be the derivative of secant squared, which would be 2 times secant x times the derivative of secant because of the derivative chain rule, right? And the derivative of secant is secant times tangent, so that would be 2 times secant squared times tangent x. Only we don't see that as a factor multiplying everything. So that's not going to be a very efficient choice of u. And that's fine, right? Like, more than anything, what I want you guys to feel comfortable with is, like, on a test, you've got a u substitution problem. You should feel comfortable guessing u, trying it out, see if it works. It doesn't work, erase it, guess again. There's nothing wrong with doing that. That's how every good mathematician does research. Think of an idea, you try it, doesn't work, erase it, start over. What's another choice of u? Just secant. Okay. What if we choose just secant? The derivative of secant is secant times tangent. And I do have a secant times tangent, but it's not multiplying everything, right? It's only part of the numerator, so that's not going to work for me either. The u choice here is going to be secant x plus tangent x. So that way the derivative of u with respect to x is going to be secant x tangent x plus secant squared x. And that is my entire numerator. So having made the u substitution, we're going to get the antiderivative of 1 over u du. And that might be your third or fourth choice of u, because it's really not obvious at all. But it's fine if you've got to guess, check, and start over. Now the antiderivative of 1 over u is natural log, so we write natural log of absolute value. Then we replace the u with secant x plus tangent x plus c for my antiderivative. Now, the only way I can remember this personally is that, and this has, by the way, nothing to do with each other, it's just coincidence. But the coincidence that I remember is that the derivative of secant is secant times tangent. So in my head, the way I remember this as a human is I think of like secant and tangent as like best friends. They're just buddies. They show up a lot. And so when I see the antiderivative of secant, I think to multiply by secant plus tangent just out of coincidence, right? Just because in my head they're buddies and they hang out together. I don't, this isn't a mathematical, logical thing. It's just, that's how I think of it. That's how I remember. And likewise, if I wanted to find the antiderivative of cosecant, you've got to multiply by something. And in my head, I think of the derivative of cosecant. Well, the derivative of cosecant is negative cosecant times cotangent. And if you don't remember that, you could always use the derivative quotient rule, because cosecant is 1 divided by sine. So you could use the derivative quotient rule. You could get there. You could figure that out. And then in your head, if you remember that cosecant and cotangent are buddies, then you could multiply by cosecant plus cotangent. And having done so, you'd get something like cosecant squared plus cosecant cotangent divided by cosecant plus cotangent. And what would be your choice of u? Yeah, just choose the whole denominator like we did last time. And then the derivative here, sorry, I didn't think it was going to be important. Well, the derivative of cosecant is negative cosecant cotangent. And the derivative of cotangent is negative cosecant squared. And so that shows up in my numerator, but with a minus sign. And then I'm going to end up with negative natural log of u plus c, but u is cosecant plus cotangent. So it's going to be negative natural log of absolute value cosecant x plus cotangent x plus c. So remember that. The antiderivative of cosecant x is negative natural log of absolute value cosecant x plus cotangent x plus c. It's in a similar vein of sort of like the tricks you wouldn't expect to use. I wouldn't have expected this until someone showed me what to do. So here, I would be completely lost. I'm like, how the heck would I take that antiderivative? That sounds impossible. But what we need to do is multiply by 1 minus sign. On the top and bottom. And if I do that, I'll get 1 minus sign in the numerator. And in the denominator, what will I end up with? It'd be what?
Negative sin squared of x.
Yeah. You get the 1 times 1, and then the inner and the outer are going to cancel each other, right? Positive sign and negative sign. And then when I have positive sign times a negative sign, I get 1 minus sine squared x. Now, the Pythagorean theorem gives us a nice trig identity. It goes like cosine squared x plus sine squared x equals 1. So in the denominator, I could replace the denominator with what? Cosine squared. And at this point, I think I would split it into two antiderivatives using additivity. What's the reciprocal of cosine? Secant. So my first antiderivative would be secant squared. And then my second one would be negative sine over cosine squared. And so for the first, what's the antiderivative of secant squared? This is one you should know. There's no tricks here. It's just the derivative of something gives you secant squared. Tangent. The derivative of tangent gives you secant squared. So that means the antiderivative of secant squared is tangent. And the second part, I would recommend a u substitution. What is that u? Cosine. And that way the derivative of u with respect to x is negative sine, and I see a negative sign up there in the numerator, so that's perfect. The antiderivative after substitution will be 1 over u squared. You take the antiderivative, that becomes negative 1 over u, and then you end up with some expression. I won't spoil the ending for you. You can figure that one out. But the trick, the moral of the story for this example that I wanted to show you for the first time is this whole thing. And sometimes I've seen books call this the trigonometric conjugate, because it kind of brings up a little bit of, reminiscent feelings of multiplying by the complex conjugate when you do dividing complex numbers, right? Except it's not a real part and an imaginary part. It's just flipping the plus or minus sign to make that happen. Okay. We got a lot of tricks to get through today. Now, we've already talked about these before in class. This is the Pythagorean identity. These are what we call power reduction identities. But these are going to be really important for you to memorize for your next test, because we're going to use them a lot today in particular. So know your power reduction, know your Pythagorean identities. We're going to use them. Today, one of the things we're talking about is integrals that look like some power of cosine times some power of sine. And so m and n are just integers. And if I've got a cosine to some integer times sine to some integer, there's a bunch of rules, and I know that this table looks really intimidating because there's a bunch of different cases you've got to cover, but the overarching principle behind this entire section is just know a few trig identities, things like the Pythagorean identity and the power reduction identities. Be familiar with those trig identities, and then also just try stuff. And if it doesn't work out, just erase it and start over and try something else. That strategy works 99% of the time, right? Like, you don't have to always know exactly what to do first. It's okay if you mess up and you try again. But in general, we'll walk through each one of these cases. Like, if you've got one of these integrals and the power of sine is odd and positive, like you've got sine to the power 3, then what you would do is you want to convert all but one of these sine factors to cosines. And what you would do, since sine is odd, is take all but one of those, so that way you have an even power of sine, and then convert those into 1 minus cosine squareds. After you make this conversion, you should be able to do a u substitution where you set u equal to cosine. And that's the goal, and that's the whole reason behind it, is because if I convert all but one sine factor, and I do this u substitution with cosine, well then I can replace the negative sine of x dx, or I should say, yeah, I'll get a sine of x dx. I can replace that with negative du, and that's the goal. So here's an example. Notice I've got an odd power of sine, and yeah, there's not a cosine here, but you can think of that as cosine to the 0 power, and you can do this with other powers of cosine in the integrand as well. But just for the heck of this example, let's do antiderivative of sine cube. And what I'm saying here is replace all but one power of x. Sorry, replace all but one power of sine with one minus cosine. And so now when we make that u substitution, we get negative 1 minus u squared du. Or u squared minus 1 du. And that's going to give you 1/3 u cube minus u, or 1/3 cosine cube of x minus cosine of x plus c.
If it was sine to like the 5th, would be 1 minus cosine to the 4th.
No. Nope.
It's always squared.
Yeah, because if this were, hypothetically, sine to the 5th power, that would be 1 minus cosine squared x squared times sine of x dx. Right? Because that's like sine squared squared, or sine to the 4th power. But 1 minus cosine to the 4th is not equal to sine to the 4th. That's a really good question. Okay. So I'm interested in checking my answer. And if I want to check my answer, I just take the derivative of my antiderivative. And then the derivative here would be 3/3 cosine squared x times the derivative of the inside function, which would be negative sine. And then that's the derivative chain rule. the derivative of cosine is negative sine, so I get something like that. Of course, this does not look like sine of x cubed, but I could factor out a sine. And if I factor out a sine, what I'm left with is 1 minus cosine squared. And now when I recognize, oh, 1 minus cosine squared is sine squared, that's how I get back my sine cubed. So that's how you check your answer. You think, yeah, that answer checks out. I got the right antiderivative. All good. The next thing in my little table, my big table, is what happens if the power of sine is not odd and positive, right? That would always work if sine was odd and positive, but what if it's not odd and positive? What if sine has an even power? What if sine is to the power 0? What if sine is to the power -1, -2? Well, then I move down and I say, what if the power of cosine is odd and positive? Well, I could do the same thing. I'll just convert all but one cosine into sines. Again, using the same Pythagorean theorem identity. I'll convert all but one cosine into sines, and then I'll be able to use a u substitution where I set u equal to sine of x. Here's an example. Find the antiderivative. I've got an odd positive power of cosine, and when I see that, I think, let me convert cosine squared into 1 minus sine squared. And I'll be left with 1 cosine. That way when I make u equals sine of x, du is equal to cosine x dx. And I see this is my du. And I can replace all of those signs and then get u squared 1 minus u squared du. And you guys know the antiderivative power rule. And you can reverse that substitution and put the signs back in. So you'll get like 1/3 sine cube x minus 1/5 sine to the 5th x plus c. But it's the same idea, you just swap the role of sine and cosine. So that takes care of a lot of integrals, right? Between the power of sine is odd, the power of cosine is odd and positive. What if those are not true? What if both powers are even and non-negative? In that case, if the powers are even, I could use the power reduction identities, and that way it'll at least bring down the power, and unfortunately it gives me a double angle. But that's better for integration than having large powers. And so instead we do that. So let's see an example of both powers being even. And I'm just going to use those power reduction identities. The 1/2 become 1/4. And then I've got 1 minus what?
What would be cosine squared of 2x?
Perfect. Yeah. So there's going to be a positive cosine 2x that cancels with a negative cosine 2x. And then when I get to the last factors or the last terms, I'll get cosine squared of 2x. Once again, I find myself in a place where I've got like 1/4 x when I take the antiderivative of the 1 minus 1/4 antiderivative of cosine squared 2x. Well, if I've got an even power of cosine, I can use that power reduction identity again. And instead of getting 1 plus cosine of 2x, this is actually cosine of 2 times 2x. I'm doubling the angle that I had before, and so this is going to be cosine 4x. The antiderivative of the 1 is going to be x. And then the antiderivative of cosine is going to be sine. And I also have to divide by the 4, right? So 1/8 times 1/4 is 1/32. All right, I think that's the answer. To double check, I'm going to use Desmos, because that might be a little bit faster than checking my answer by hand. And so what I'll do is I'm going to plug in the first case, y equals the integral from 0 to x of cosine squared t. And I think Desmos wants me to use parentheses, so I will. Times sine squared of t dt. And on the other hand, I'm going to type in y equals 1/8 x minus 1/32 sine of 4x plus c. Add a slider c. And so if this is correct, I should be able to choose some c in my antiderivative to make this match up. Sure enough. There we go. So that's one way to check your answer. So sometimes you have to repeatedly apply the power reduction identity. But I eventually got there. Questions? Easy so far?
Repeat it until there's like no cosine squared.
Yeah. Because we don't know what to do necessarily, like how do you take the antiderivative of cosine squared? But if we get rid of the squares, it's easier to take the antiderivative of just cosine. So here we go. Let's talk about our table again. The next row in our table says something like, what if the power of sine is not odd and positive? The power of cosine is not odd and positive. What if both powers are not even and non-negative? Well, the next thing you might come across is, what if both powers are negative? In this case, we want to multiply the integrand by cosine squared plus sine squared, because that's like multiplying by 1. And then where that plus sign happens, we can split this into more than one antiderivative. Like in this case, I can write that 1 in the numerator by writing cosine squared plus sine squared. In the denominator, I've got cosine squared x times sine of x. And what I mean by split the integral is I mean in one case, I'm going to have cosine squared x divided by cosine squared x sine x. And in the other, additivity allows me to write just sine squared x over cosine squared x sine x. So for the first antiderivative, the cosine squareds are going to cancel. I'll be left with 1 divided by sine and 1 divided by sine is cosecant. And the antiderivative of cosecant is going to be negative natural log of absolute value my brain just blanked. Is it cosecant x plus cotangent x plus c? Is that it? Yeah, okay, we got it. We got it. We got the first one. The second one is sine squared divided by cosine squared divided by sine, which is sine divided by cosine squared. This is secant times tangent. And the antiderivative of secant times tangent is secant, just because I remember the derivative of secant is secant times tangent. And so I only need 1 plus c for my final answer here. Sorry, there's an equal sign that shouldn't be there. It should be this.
For the one in the purple, sine of x over cosine squared of x, could you also do a u substitution there?
Yeah, a u substitution would work. I'm even getting kind of deja vu. I think we talked about using a u substitution less than 30 minutes ago for that same problem. Okay, so that was pretty tricky. I mean, that was pretty tricky. The main thing that I wanted you to learn from this example, the reason this is in my lecture notes, is because I don't know what to do when I see the antiderivative of 1 divided by cosines and sines. But rather than panic, I think the easiest way to sort of make these negative powers, and I'm calling them negative powers of cosine and sine because they're in the denominator. The easiest way to make these negative powers, interact again with the numerator is to multiply by cosine squared plus sine squared. And then that allows you a chance to break up your antiderivative and hopefully find something that's a little bit more simple, tractable. All right. In case you weren't already overwhelmed, there's more rules. Like, what if you come across an integral where the integrand has some power of secant times some power of tangent? Remember I told you secant and tangent are best friends and they go around everywhere together? It says memorize the following identity, but that's not 100% necessary. If you have the plain old homemade vanilla Pythagorean identity and you divide the whole thing by cosine, what do you get? I should say cosine squared. Divide the whole thing by cosine squared and you would get 1 plus tangent squared equals secant squared. That's going to be important whenever you come up with these kinds of integrals. And we have more rules that look like if, then that. Like, what if the power of secant is even and positive? Then we're going to want to convert all but one secant squared factor to tangents, leaving one of the secant squareds behind. That's what we do if the power of secant is odd and positive. So let's do an example of that. Here's one where the power of secant is even and positive. I think I said odd. The power of secant is even and positive. And so I'm going to convert one of those secant squareds into 1 plus tangent squared. I've got a tangent squared from my original numerator, and then I'm leaving behind one of the secant squareds. I'm leaving behind one of those secant squareds on purpose because for my u substitution, I'm going to choose u equals what? Tangent. And if u is equal to tangent, the derivative of tangent is secant squared. And so I will be able to replace secant squared dx with du. And that's the whole purpose. That's why I wanted to leave behind one of those secant squareds, is so that now I can write 1 plus u squared times u squared du. And then my final answer is what I get if I do my antiderivative power rule and I replace the u's with tangents. I get 1/5 tangent to the 5th x plus 1/3 tangent cube x plus c. This is what you do if the power of secant is even and positive, and you may or may not have some power of tangent. And you notice this method would be the same whether this was tangent cubed or tangent to the -3 power, or if that tangent wasn't there at all. You'd still want to use the same strategy, which is convert all but secant squared into 1 plus tangent squareds. And then u sub u equals tangent. Okay, next thing in this big table says, okay, what if the power of secant is not even and positive? Maybe the power of tangent is odd and positive. So let's find one where the power of tangent happens to be odd and positive. And what I'm going to do, if the power of tangent is odd and positive, is I'm going to convert as many of the tangent squareds as I can into secant squared minus 1. And I'm leaving behind one tangent for a good reason. So in addition to converting a tangent squared into a secant squared minus 1, I also split up secant cubed into secant squared and an extra secant towards the end. You'll see why here in a minute. What do I choose for u? Secant. So if I choose u equals secant, then du becomes secant times tangent dx. And that's exactly why I wanted to leave behind one tangent factor, and so that a secant times a tangent can be part of the du during the u substitution. So I get to rewrite this thing as u squared times u squared minus 1 du. So I will get 1/5 secant to the 5th x minus 1/3 secant cube x plus c. By the way, something really weird happens if you were to have an integrand that looked like secant to the 4th times tangent cube of x, where you could do the secant u substitution, or you could do the tangent u substitution. You've got a choice on which one you want to do. You'll actually get an antiderivative that looks different but is exactly the same. And if we have more class time at the end, maybe I'll show you that. But there are ways of like sort of stumbling across trig identities, because you will get the same antiderivative, but it might look different.
So if it's like odd, you use tangent squared, and then if it's like even, then you'll use secant.
Yeah.
Okay.
I mean, you got a printed copy of my notes, so you can refer to those later if you need to. I'll tell you, in reality, like I don't have those rules memorized at all. In the situations where I need to know how to take one of these integrals, I just try stuff, you know? I just attempt to make some u substitutions. I just attempt to replace some stuff with the Pythagorean identity. And if it doesn't work, I just erase it and start over again. It's a little bit more time consuming that way, but I'm just not great at memorizing. So that's just me. So we covered, that last example was an odd power of tangent. Now what happens if the power of tangent is even? What we could do is convert only one tangent squared factor. So let's see what that looks like. If we convert only one tangent squared factor, we're going to want to do that in the case where I have an even power of tangent, like if I have tangent to the 4th. And I've got the knowledge that tangent squared is secant squared minus 1. Yeah. So what it looks like to convert only one of these tangent squared factors is it's going to be tangent squared times secant squared x minus 1. And I'm going to split this up using my additivity property. In this first integral, I can solve this with u substitution, where u is set equal to tangent. Because if u is equal to tangent, du is going to be equal to secant squared dx. And that means u squared du For the second integral, this is once again a case where I have an even power of tangent. And like my table tells me, if I have an even power of tangent, I'm going to replace just one tangent squared factor with secant squared x minus 1. So this becomes 1/3 u cubed. And then this over here becomes, I don't know, what's the antiderivative of secant squared? Tangent. Very good. And minus -1 is +1. Antiderivative is x. So you kind of whittle it down when you have an even power of tangent. Like if I had tangent to the 6th power, then it would probably take 3 steps of replacing just one tangent squared factor instead of 2 steps like this time. Okay, did we cover all my rules yet? What if the power of secant is odd and positive? This would be horrible, and so we are not going to put this on a test. You don't have to worry about an odd positive power of secant. Unless, I could give you an odd positive power of secant if there's a power of tangent that's even and positive, right? Or if there's a power of tangent that's odd and positive. But I'm talking about the cases where secant has an odd positive power and there's no tangents there to fix the solution for us, then, that's really hard. Like if you have the antiderivative of secant cubed, for example, that takes an hour at least to work through that problem. It's tough. It's not impossible, but it's really crazy, and we wouldn't put that on a test. If you have some other combination of powers, the thing you could do is you could try to convert your secants to 1 over cosines and your tangents to sines divided by cosines. And then you refer to your earlier table in my notes where we had integrals of sines and cosines, right? And maybe that could work out. What about this example? I've got secant to the positive 1 power and tangent to the negative 2 power. That might fall into the category of convert to sines and cosines. Let's try it. Secant is 1 divided by cosine, and tangent is sine divided by cosine. So tangent squared in the denominator is going to become cosine squared over sine squared. What do I choose for u this time? What?
Sin of x.
Mm-hmm. What's the antiderivative of 1 divided by u squared?
Cosecant squared.
1 divided by u squared would be 1 divided by sine squared, which is cosecant squared. But I'm talking about just take the antiderivative, right? If you have u to the negative 2 power, what's the antiderivative with respect to u?
-1/u.
Yeah, negative 1 over u. Now u is sine. What's 1 over sine? Cosecant. So that's what I mean if I say, convert from secants and tangents to sines and cosines. That's something you can try. The last thing I'll leave you with is the last page of your notes. If I had my plain vanilla Pythagorean theorem identity, and I choose to divide everything this time by sine squared, what I would get is this. Because cosine divided by sine is cotangent. Sine divided by sine is 1. 1 divided by sine is cosecant. So maybe we come across an integral that only has powers of cosecant and cotangent. And then there's a whole bunch of strategies you could learn for dealing with powers of cosecant and cotangent. But the great trick about this table of stuff is that it's exactly the same as how you would treat secants and tangents. Cosecants and cotangents behave exactly the same as secants and tangents. So you don't have to really learn anything new. Earlier we talked about what happens if the power of secant is even and positive. Now we're talking about what if the power of cosecant is even and positive. And it looks exactly the same. We just put co in front of everything. So it's not actually learning any new strategies. And like I said anyways, I don't even remember these. If you were to just hit me with one of the questions off of your homework, I'm just more of a guess and check kind of guy. I'm just going to try something and hope that it works. When it doesn't work, I just, try again. But what are your thoughts? Questions? If you look at your test review page, are there any questions you want to work? We still got 10 minutes of class. If you want to see something else.
I think I'm just forgetting, but on the last example, how did the 1 over u squared, what do you think the antiderivative of that become 1 over, negative?
Mm-hmm. That's a good question. So 1 over u squared is u to the negative 2 power. So if I have an antiderivative of u to the negative 2 power, I go up when I take an antiderivative, so I'm going up from negative 2 to negative 1. And then with the antiderivative power rule, I divide by the new exponent, so I'm dividing by a negative 1. And that makes it negative u to the negative 1, which is negative 1 over u. I just can't believe we got through this. I saw like 17 pages of lecture notes, and I thought that this would take way more than 75 minutes, but we kind of zoomed through it. So let me show you something. Let me show you something that I think is at least mildly interesting. You know, we were talking about something like, oh gosh, I gotta find it. We had one set of rules for when secant is an even power, and we had another rule for when tangent is an odd power. But what if secant is an even power and tangent is an odd power? What if I have something like secant to the fourth tangent to the third? We're going to solve this thing two different ways. On the one hand, I could replace secant squared with 1 plus tangent squared. And I would still have a secant squared left over, so that way when I do my u substitution, I can choose u equals tangent du equals secant squared dx, and I will get 1 plus u squared times u to the third du. And then that's u to the fifth plus u to the third. And then we take the antiderivative and we replace u with tangent, and I find 1/6 tangent to the sixth x plus 1/4 tangent to the fourth x plus c. Okay, alternatively, I could see that tangent has an odd power, and I could replace all but one tangent with secant squared minus 1. So let's do that. I'll have secant to the fourth x, which I could replace with secant cube x, and then tangent cube is going to be secant squared x minus 1 times an extra secant times an extra tangent dx. This time my u substitution will be secant, and that means du is going to be secant tangent dx. So I'll get u cubed times u squared minus 1 times du, which is u to the fifth minus u to the third. And taking the antiderivative and replacing u with secant, I get 1/6 secant to the sixth x plus, no, minus 1/4 secant to the fourth plus c. And so we took the antiderivative of exactly the same integrand two different ways. And it looks like we kind of got two different answers. But antiderivatives are unique up to the constant, right? Whatever you choose for the constant. So these must be the same. And I think that's kind of weird. We could check and make sure they're the same. And type in y equals 1/6 tangent x to the 6th power plus 1/4 tangent x to the 4th power plus c. And then we'll type in on the other side. The plus c's do not have to be the same constant, by the way. Right? Antiderivatives are unique only up to a constant. So I could have a different constant in these two antiderivatives, plus 1/4 secant x to the 4th power, and, oh, I need an x there. No, minus. There's a plus sign, but it should be a minus sign. And this is what it looks like when I plot my two answers together. To get these curves to match up exactly, all I have to do is tweak the constant I'm multiplying by. Or sorry, not multiplying. I gotta tweak the constant that I'm adding to the end here. So that I get this curve on top of that curve, and bam. With the right choice of constant, I can make these match. Looks like it's negative 0.09, 0.08. Something like that. But like I said, not terribly interesting, but a little bit mildly interesting that you can get two antiderivatives that look different, but they're both correct answers. And so I always try when I grade these tests to be very careful about grading. Otherwise, it could be really easy to take off points, right? If my answer key has tangents, but your answer has secants, maybe you got the answer right. Maybe I got to slow down and grade more carefully. Because there's often more than one way to skin a cat.